Welcome to the final exam, question number 10. It asked it says the advantages of continuous beams over simple beams include, so let's just write these down. 1, 2, whoops, that's not 2, that's 3. 2, 3, 4, and 5. And we'll cross them out as we come to them, or say yes. I'll give them checks, or I'll cross them out. Let's change colors here. Let's go with the purple. No pink. We haven't used pink in a while. All right. So, in case you remember what a continuous beam's, I'm going to run this over. Of course, going faster, hopefully you know what these are, but in case you don't, a simple beam is like so. A continuous beam is when you have continual supports. But this beam, it's one beam. So this is one beam, or it's at least got a diaphragm, has a diaphragm, not got a diaphragm. It has a diaphragm that connects and makes that one beam. And in this case, this is a simple span. You can also have, for instance, the railroad does this often. You can have, let's say this is a bent or a cap. Obviously this is a diagram, so it's an imperfect, of course. So it doesn't mean that it has to be a single span structure to have a simple span. Or if we're doing railroads, let's make the abutments look like that. All right, for instance, and this has piles coming down, and it says piles coming down, piles coming down, and it's all steel pile. Maybe you have some battered piles in there. All right, and here's your, trying to throw some real world examples in there. There's your stream, and usually it's about a foot up. There we go. So, of course, these are closer together. These are like 2 inches or 4 inches apart, depending on what you're trying to do. And then I'll have a plate sitting over, a real thin steel plate, covering that little bit of hole. And if it's a ballast bridge, you'll have this is looking at very simple. You'll have a ballast on top. I'm sorry, I'm getting into it a little too far. The fact is, this is a simply supported beam. This is simply supported span. This is simple support. This is another simple support. This is another simple support. You don't have this. You don't go in here and pour a diaphragm, and these girders don't have little rebar sticking out to make this. Once you come in, you pour this, and that's all of a sudden a continuous span. You don't do that on railroads. You want simple spans. And most of the reason being that you want to get in there and be able to switch it out real quick, and you would have to wait 28 days, or it could be fast drying concrete for that to work. But they usually have to get this down in if you have a track window of an hour or 4 hours. You need to get in there and get it in, get it out. You don't have time to be pouring any concrete. All this stuff has to be pre-made or prefabricated. All right. That's enough. I need to stop talking. Sorry. Sometimes I get out of control and start just talking. The fact is, simple span is like so. And a continuous span is continual over these supports. These are supports right here, and it's continuous. So what are the aspects of this? And one thing you can take a look at, and it would be extremely helpful to take a look at, would I'll guess I'll just go ahead and answer the questions based on my knowledge and go from there, and then we'll slowly skip through this section. There it is. And you can see mathematically why it is. But what this is going to end up doing, if you want to look at a moment diagram, is this will go like that, and it will be positive moment the entire way. I mean deflection. We're looking at deflection. At this point, it'll deflect like that, like so, like so, like so. And you'll look at a moment diagram of this. So we'll do moment diagrams in yellow, I guess. This moment, and this will look like. Is this right? I believe this is right. Don't hold me on this. All right, positive moment. And then this will have positive moment, and then it'll be a negative spike, positive moment, negative spike, positive moment, negative spike, positive moment, negative spike. Or actually it'll go to 0 right there. That might just delete the whole darn thing. Shoot. Positive moment, then it'll come down negative, positive. And this is for a uniform dead load. And it'll go to 0. Obviously, if you have, a truck sitting somewhere, that's going to increase and decrease as is. But if it was a uniformly distributed load on this, that's kind of how it will work out. And in this, it would deflect on the they'd be individual, so it would deflect, it would stop. This is completely individual. It's not tied together. Completely individual. And obviously, depending on where the train is, it's going to dip down even more when the train comes across. And you have your pretty simple moment diagrams right there. And as you can see, those match up exactly with this simply supported beam up here. All right, on to the question. One says less deflection. And I know that doing this continuous support, it actually helps you out quite a ways as long as you balance your spans accordingly. And so I know that it does give you less deflection. So I'm going to say check. It says lower moment. Yes, that's another positive. Less shear. No, this is incorrect. Despite the moments, it helps you out in moments. It does not help you out on shear because that's distributed pretty much the same. Then simpler calculations, absolutely not. Continuous is much more difficult than simple span. And then simpler, if that's a word, construction details. I would also say negative on that. Definite negative on those two. Because these construction details, the simple span is pretty simple. Okay, you have a bearing. You'll have a bearing here. You have a beam. You plop the darn beam down on top. You don't connect it, you're good. Beam, bearings, good. Beam, bearings, good. Typically railroad bridges are pretty darn simple. It's more like an erector set. These, on the other hand, the details get ugly. You have to have negative reinforcing now in the slab. You need to make sure that negative reinforcing regions over here are taken care of, and it gets nasty. The math on these continual slab are much more difficult than a typical railroad design. And when I say typical, because typically these are what, let's say, don't hold me to this, 28 foot. This will be 28 foot. You go in there, they already have this designed. They know exactly, hey, we have a 28 foot box culvert or box beam that we'll use all the time for that simple span, and it will always be that. All right. So we have to figure out one with 1 and 2. What has 1 and 2? A has 1 and 2. So the answer to number 10 is A. And I said I would kind of go to a mathematical way of looking at this, and you can go to page 2-312 in your steelbook, and they actually have these continuous beams, moments, and shear coefficients equally spanned, equally loaded. And they have uniform dead loads, and you can see what the moment is in terms of WL squared. So if we have this is in terms of WL squared. Well, we know that the moment is WL squared over 8, correct? So this is what? Let's say this is a 4 all equally span bridge. So 4 span, 1, 2, 3, 4. We go down to 4th, and we can say that the positive moment in this, let me change colors, in this region and this region will control, and they are, what is it, what does it say, 0.77? No, that's 0.077. And this is in terms of WL squared. So what that means is you should multiply this by WL squared. So we know that, let's do an equivalent here. Let's say you have four. This is actually a 4 span bridge. So make this bridge 4 simple spans, like a railroad, and then we look at it as 4 continuous spans. Let's say they're each, 10 foot, 10 foot. Let's just do this for simplicity. 10 foot, 10 foot. And we have a W equals 100 PLF. Obviously, very, very unrealistic, but that's okay. We're just doing this to show what we get. So if you have, let's see what your maximum moment for your simple is M equals WL squared. This is 100 PLF. L is 10 foot squared over 8. And that equals 100 times 10 squared divided by 8, 1250. 1,250 foot-pounds. All right, now let's look at this. What is 0.077 WL squared? Equals 0.077 times W, which is 100 times 10 squared, equals 770 foot-pounds. And as you can see, when you make it continuous, it's quite a bit less, actually. It's about, what? 1250 divided by 770 is 1.62. Let's do 770 divided by 1250. It's 60% of that, so you get to chop off 40%, which will help out a ton if you're thinking about it. As long as you can deal with this negative moment regions, then you should be able to deal with that. All right, I hope that helped get a little concept of why things are continuously loaded, because as you can see, once you go down, that 0.75 or 78 is kind of maxing out. That means it's never going to get any different. And anything you get over, then what is it? 1, 2, 3, 4, 5, 6, 7 spans. The end spans stay the same, and then all the interior spans stay. I think everything stays the same. I hope that makes sense what I'm trying to say. All those, you can have 12 spans, and it'll be similar to that last one on the bottom. All right. I hope that makes sense. That's a numerical example of why this continuous beam is smaller than the simple span moment. Continuous moment smaller than simple span moment. All right. I hope that helped. I will see you in question number 11.